the last presentation before the lunch break with Airbus Protect. Daniyah Rafique, the system engineer, and he will give us some insights about hydrogen infrastructure and the challenges for hydrogen planes. Please. She, excuse me.
Thank you very much. So the last question, they were talking about infrastructure in airports, and I think this is a great way to introduce my presentation, which is hydrogen infrastructure and their challenges for hydrogen aircrafts. So first, thank you for coming to this presentation. And hopefully I can introduce some new aspects, but if not, develop on some of the aspects we have already about hydrogen infrastructure and what is needed for the hydrogen planes. So the first here it is. Thank you. Perfect. So the first thing we're going to do is give a bit of background into my experience with hydrogen infrastructure and also hydrogen airplanes, and then go on to Airbus Protect, who I'm employed with. After that, I'll introduce some more hydrogen infrastructure concepts, feeding into some technical aspects from production all the way to end use, and then discussing some of the external challenges such as legislation, technology maturity, and market availability. That is a picture of me with the mobile compression unit, which I developed as a process engineer for 2 years with a company called Logan Energy. And this hydrogen mobile compression unit takes low pressure hydrogen at around 30 bar gauge and compresses it up to 700 bar gauge. And applications such as this, so this unit here was used to refuel hydrogen buses in Scotland, and also used to refuel a hydrogen plane also in the UK. So as you can see, there's already a demand for trialling these new hydrogen vehicles in the UK. And outside of just the compression unit, I also worked with the production, so using electrolyzer systems to produce green hydrogen, and also road certified compressed hydrogen storage. So once you produce the hydrogen, taking it from the production site, preferably storing it at high pressure, because once you store at high pressure, you're storing more of hydrogen, and transporting it to the customer site. I also worked with fuel cell integration in the marine industry. Lots of UK funding grants are given to the marine industry to develop net zero emission vehicles, which is important because the shipping industry does contribute a lot to carbon emissions. And here's some information on Airbus Protect. And our motto is enabling a trusted future. If you're wondering what that means, I'm also wondering what that means. But basically, with Airbus Protect, we are a subsidiary of Airbus. And we support Airbus within safety, sustainability, and cybersecurity. Those are our 3 pillars. But we also support external companies. So this is also involved with hydrogen supply chain. Because if we support the supply chain, we're also supporting Airbus. And that is one of the key messages that we would like to give, is that if there is any need for sustainability, cybersecurity, or safety, then Airbus Protect can help. And in the context of hydrogen, within the Zero E program, we have employees that support in a variety of roles, from designing and procuring test benches to investigate liquid hydrogen behaviour, to supporting safety activities for the certification of the Zero E aircraft by 2035, and designing liquid hydrogen tanks and distribution systems. So we really want to support the full design aspect of the Zero E program, and with this experience, also support the supply chain. So now that we've moved on from the brief introduction into me and Airbus Protect, I think the best way to introduce hydrogen infrastructure as a concept is taking it step by step from the production, which here is the green hydrogen production, which we hope to use, and which is the main basis of why we hope to produce the liquid hydrogen plane, is for zero emissions. And so this electrolyzer is a unit which takes water in, very, very pure water, and splits it into hydrogen and oxygen. And in order to produce green hydrogen, you would preferably put this in a solar farm or a wind farm, in which excess electricity that can't be exported to the grids will then be used to produce hydrogen. And this is already being done around Europe and in the UK. And then from this, you take the hydrogen from the electrolyzer. But the problem is with these electrolyzers is that they produce hydrogen at a low pressure of around 30 bar gauge. And if you're wanting to transport it, ideally you want to transport as much hydrogen as you can in a storage container and then give it to your customer. So what we have here for the filling station is a unit which compresses from low pressure, so 30 bar, into something higher pressure, about 200 bar gauge or 300 bar gauge, to be stored. Then it's transported from the solar farm or wind farm to the customer site. And assuming in the use of a hydrogen plane, and specifically for Airbus, which is using liquid hydrogen, you'd need to liquefy the compressed gaseous hydrogen into liquid hydrogen. And this unit will then be transported to the hydrogen refueling station to refuel the hydrogen plane. So this first concept that I have introduced, you may be thinking, why can we not just produce liquid hydrogen at the solar farm or wind farm? Why do we have to compress it, transport it, then liquefy? And that is a very good question because this is a very inefficient system. Ideally, if you could liquefy it at the start, you should, to reduce the unnecessary filling or compression unit. But the problem being is that currently there are not many applications for liquid hydrogen because the liquefaction system is very, very energy intensive and expensive. And so these solar farm owners or wind farm owners would much prefer to buy a cheaper infrastructure, in this case compressing the hydrogen and selling it off to hydrogen bus refueling stations, which have a greater demand currently. But in saying that, there are arguments for liquefying at the start, as I mentioned before. So this is the second concept that I'm introducing, which is liquefying it instead of compressing it. And this is a much easier and preferable solution, especially when you're transporting it to the aircraft. You'd rather have the liquid hydrogen available for you to just refuel into the aircraft rather than having to go through this additional step of liquefaction. But as I said, this is a more of a question of, if we do have hydrogen available, then how is it available? So we shouldn't demand too much because, unfortunately, liquid hydrogen may not be available for us to use on aircrafts. But I discuss this topic more in depth later on. So I introduced the first block within the hydrogen life cycle, which is the production of hydrogen. And currently, a lot of electrolyzer companies are struggling with the scale-up. A few years ago, they were making kilowatts of electricity input for electrolyzers. But now with the ramp-up of the hydrogen industry, they're now having to make megawatts. And many of these PEM and alkaline electrolyzer companies cannot make that transition. Actually, there was a good quote from the chair of ITM Power, which is a major electrolyzer manufacturer, and they said that they underestimated the competencies and capabilities required to scale up and transition from an R&D company to a volume manufacturer. And it's not just PEM electrolyzers, it's all alkaline electrolyzers as well that are struggling. Because it's not just the manufacturing capabilities that they're struggling with, it's the design capabilities. They're now having to scale up the stack and the balance of plant to support this production, but then they're having to change the cooling demands of these units because they require a greater heat rejection. Another problem with this is that with the hydrogen boom, they're having to produce more. But in producing more, they're also having to repair previous existing electrolyzers that have been damaged. So they have this list of many, many orders that customer wants, but at the same time having to repair their old electrolyzers that they have produced. So it's only creating more and more problems for them. Another big question, and one that I've dealt with personally, is the safety aspect. Many of these wind farms or solar farms are located in isolated areas. And so because it's an isolated area, you can't have operators looking and making sure it's all operable. So instead, we need to discuss is how can we guarantee safety? How can we ensure that our processes are robust enough? And how can we ensure that if there is no one on site, that the system is capable of shutting down and going into a safe state? And this monitoring control system that I've talked about is very, very difficult to design because it involves multiple partners, such as safety bodies, to guarantee what you are designing is correct. Another part is logistics. So with these wind farms or solar farms that have produced the hydrogen, a problem for them is who do we sell it to? And what you'll have is competition of many, many people that are wanting to buy the hydrogen. But of course, there's only so much that can go around. So I talked a little bit about previously is the storage of liquid or compressed gaseous hydrogen. So liquid hydrogen is stored at negative 253 degrees Celsius at 1 atmosphere. And the benefit of storing liquid hydrogen is it's a higher density material. So you can store much more with liquid hydrogen than you can with compressed gaseous hydrogen, which is one of the biggest concepts that many aviation leaders choose liquid hydrogen over compressed hydrogen. So for 5 kilograms of liquid hydrogen, it can be stored in 75 liters compared to compressed hydrogen, which 5 kilograms of that can be stored in 125 liters. And but the benefits is that there's a balance that you have to find with this. There's not one solution of you can store liquid hydrogen for this application or that. It's really discussing the distances that you're having to travel with your hydrogen. So for liquid hydrogen, it will have some boil off, not a lot, but the more you store it, the more it will boil off eventually. And it is more costly in shorter transport distances than compressed hydrogen. So for example, if we were to look at the dollar per kilogram of H2, currently for storage, it costs $167 per kilogram of H2 for a liquid trailer, compared to $783 per kilogram of H2 for a gaseous trailer. So LH2 storage is cheaper, and you're storing much more. But this is only for shorter distances, which makes it viable. For longer distances that make it viable. But if we were to look into the liquefaction process compared to the compression process, liquefying hydrogen is much more expensive. And this is because with liquefying hydrogen, you're having to have a series of nitrogen and helium heat exchangers to cool it down to its inversion point. And this inversion point basically changes the characteristics of hydrogen, in which when you now expand hydrogen at its inversion point, it will cool down and eventually reach the liquid state. And many big companies like Air Liquide or Linde use this process, but it's very, very energy intensive and requires lots of control and monitoring. And roughly it takes about 3 times the energy compared to compressing hydrogen to 700 bar. So as you can see, it's very, very energy intensive, expensive. And this is another reason why many wind farm and solar farm owners prefer to compress. It's cheaper. And another task is, how do we transport this hydrogen? So either road, marine, or train, maybe by plane. But the biggest challenge is, of course, certifying your storage tanks to be able to transport it, and also maintaining these cryogenic temperatures, because it is a very, very, very cold material, negative 253 degrees Celsius. So you need to ensure that your insulation is keeping it at that temperature, and also ensuring that the safety concerns of what if the insulation is damaged, how do we maintain a safe aspect of that design? And the next aspect is the hydrogen refueling station. So you would think it's a simple process. You get your liquid hydrogen and you just fill a plane with it. Unfortunately, it's not that simple. Otherwise, I wouldn't have a job. It's a very complex system that involves an interface and communication between the refueling station and the plane. Because if you're thinking of the safety aspects, the most important thing is that you don't overfill the tank. Because if you overfill the tank, you have liquid hydrogen coming out, and if it's at an airport, then that's disastrous, obviously, and there's a risk of ignition and possible explosion. So what you need to do is maintain an interface and communication between the plane and the hydrogen refueling station. And this could be involved with the tank level transmission. So you monitor the tank within the plane, and you send it to the HRS so they know exactly it's reached its maximum level. Okay, we should stop refueling. Similarly, for emergency shutdown, it's important that these systems, if you were to trigger one shutdown, then all the systems involved should be shut down. For the interface coupling, so the coupling that connects the refueling station to the plane, you have the mechanical interface, which involves potentially a valve to ensure that there is no emptying of liquid hydrogen when there is no connection. But also this could involve the interface coupling to allow the communication between the plane and the HRS. And I mentioned earlier, it's not as simple as filling the plane. There is a purging sequence that has to be done to make sure there's no air within the system. Because if there is air within the system, you could introduce hydrogen into the system and create an explosive mixture. And with hydrogen, you only need about 4 volume% in air to create an explosive mixture. And of course, the filling sequence, which I mentioned before, we need to ensure that it will not overfill at all. Moving on to external factors, one of the main reasons why companies aren't incentivized to pursue hydrogen technologies is because of the lack of legislation for the approval of hydrogen as a primary fuel. So currently, in many aspects with YASA or the marine industry, there is no legislation, and it makes it difficult for you to develop technologies because there isn't a skeleton format which you can fall back on to design your system. And in many of these cases, this causes an even more expensive process because you're having to continuously discuss with multiple parties on how best to design a system. And many parties involved will have a different idea how to design. And if you don't have legislation to sort of come to a conclusion, then you're spending lots of labor discussing the design. Next is the technology maturity. There are very few cryogenic hydrogen components, and the few components that are in development are very expensive to buy, which isn't incentivizing anyone to go into hydrogen. And the few components that are available, they're having to test continuously to prove that is safe enough or reliable enough to be used within the aviation industry. And that brings another point is, how can you test these cryogenic components? Currently, there are no testing infrastructures available, so it's even more expensive. And that's something that I think many people need to develop, is the test benches, the infrastructure to allow these components to be tested and used within the aviation industry. And going on to market availability, which is similar to what I discussed before, not many people want to get into the aviation industry with hydrogen because currently we want to buy 5 to test it and it's costing them a huge amount of money to even make it and sell it. So, why would they want to get into this market? And because many of these people that are wanting to develop, they're only potentially in it for IP because they see that in the future there could be a greater demand and they don't want to share this IP, which is prohibiting growth and innovation. So this is a quick reflection on external factors, which also, along with the technical factors, are inhibiting the growth within the hydrogen aviation industry. So that is it for my presentation. Short and sweet, and I can go into questions. Okay, yep. That is a very good question and one that I can't answer. But if we were to go back, so say we take this example. So the electrolyzer, say it runs about 50%, because not all of the electricity you input will be there to produce the hydrogen. The liquefaction unit, I think maybe 40%. So you're looking at below 50% for majority of these units. So it's a very, very inefficient system. And if you're looking into the filling station, that's not really that much of an expensive unit. It's just taking what's being liquefied into the storage unit. You're transporting it, and then the hydrogen filling station, you're just basically converting it. So I'd say the electrolyzer unit around 50%, and the liquefaction unit is about 40%. So it is a very inefficient system. Yeah. Any other questions? Yeah. Okay, good question. So this gentleman asked if it's more efficient to produce at the airport than having to do it at a solar farm. Ideally, yes. If you were to transport it at shorter distances, then of course it's more efficient. But the problem is how are you going to create this green hydrogen? Because there's not going to be a wind farm at the airport that can produce this green hydrogen. And also, there are many challenges with airports. There's a lack of space, first of all. And also, if you are going to produce hydrogen, it's going to be very, very difficult for you to get certification for even putting this infrastructure there because of the potential for catastrophic effects if there is an explosion. Any more questions? Okay, great. Thank you very much.
Thank you, Ms. Rafique. Actually, I'm just curious to know, you mentioned that the hydrogen produced is going to be transported via trucks, by train, by marine, and I'm just wondering if they are using sustainable propulsion. I mean, if the truck is working with diesel, then the blue value chain is disrupted somehow.
Yes, that's a very good point. Ideally, for anything you're transporting, it would be an electric or zero emissions vehicle. And hopefully it can be used. I know in some projects they're looking at using hydrogen trucks for transportation. So when they're filling up their storage containers, they're also filling up the hydrogen tank in the truck to produce it as it goes. But of course, with the inefficiencies with hydrogen, it's very, very difficult to do this.
Thank you. So still a lot of hurdles for the hydrogen, but it's on its way, I'm sure. And this actually brings an end to tomorrow's session, and we continue after the lunch break with additional interesting presentations both on both sides, in parallel here, and just opposite on the other side, you see about who is going to present. You see on the screens which are located just behind you. So thank you very much and have a great lunch break. Thank you.